All right, so let's continue with the series. But do you notice something weird? Instead of talking about series as part 2, I got logic. Yep. I need to cover some basics of logic for your benefit. Okay, let's get on with it. Definition. A proposition is a statement that is either true or false. Right? A proposition is a statement that is either true or false. Any examples that you can think of? Pause the video if you need to and think of some statement which you can say, hey, that's true, or no, that's false. Right? Okay. Washington, D.C. is a capital city of United States. Is that a proposition? Well, can you answer that with true or false? Washington, D.C. Yep, that's a statement. And in fact, this is a true statement. Right. Another example. 2 plus 2 equals 22. Is that a statement? Yeah, we can answer whether 2 plus 2 in fact equals 22. That's true or false. In this case, it turns out to be false. Right? Wait. I should have added something else. What is not a proposition? Hello. Is hello a proposition? Can you answer hello with a true or false? Is hello true or false? Doesn't make any sense. Yo, what's up? Is that a proposition? No, because you cannot answer true or false. Right? So let's move on. A conditional is a proposition of the form if P, then Q. So a conditional is also something which you can answer as true or false. And its form happens to be if P, then Q. What are P and Q? They are propositions themselves. In fact, one good way to read this is, if P is true, then Q is true. Typically, philosophers and logicians do not say P is true. If they say if P, then automatically it is understood that P is true. So if P is true, then Q is true. This is another way of writing a conditional. You can write this as P implies Q. You notice that when I solve problems, I keep using implies quite a bit. Basically, what I'm saying is, when I say x equals 2 plus 3 implies x equals 5, what I'm saying is, if it is true that x equals 2 plus 3, if that statement is true, then what follows, x equals 5, must be a true statement. If the previous is true, this is true. That's why I have an implies in between. Cool? So if P, then Q. If X is a poodle, then X is a dog. Is that a conditional? Yep. Is that true? If X is a poodle, then it must be a dog. Right? So that is a true statement. Now, let's see. If x equals 2, then x plus 3 must equal 7. Is that in the form of if P, then Q? Yep, it is. P is x equals 2. Q is x plus 3 equals 7. If P is true, is Q true? No. If x equals 2, then x plus 3 should equal 5. And this one says x plus 3 should be 7. So this is false. Right? This conditional is false. All right. A converse of a conditional if P, then Q is also a proposition, and its form is if Q, then P. You reverse the P and Q of the conditional. If Q, then P. Cool. Now, can you tell me what the converse of this conditional is? If X is a poodle, then X is a dog. understand one thing, please. The commas, the if, the then, they all must be present. If X is a poodle, comma, then X is a dog, it's got to have that kind of a form. Okay. Now, what do you think is the converse of this conditional? Would you agree? If X is a dog, then X is a poodle, right? That is the converse. So, by the way, converse is Q implies P. So thus the converse of X is a poodle, then X is a dog is, if X is a dog, then X is a poodle. Is that true? Now, please pay extra special attention to what I'm about to say. You have to say this statement is false. Now I know. You will say, why? It is possible that I pick a dog and in fact it is a poodle. So that statement is true. Yes. The fact that you can provide a gazillion examples where that statement is true means nothing. If I can provide one measly counterexample, can I do that? Can I pick up a dog and turns out it is not a poodle? Yeah, I could pick a Labrador and that is definitely not a poodle. So the fact that I have come up with one counterexample is enough to say that this statement is false. The reason people say the statement is false is immediately you know that you cannot make use of this as an argument in a logical setup. That's why people say false. In some cases it is true. Yes, that's a different story. But what we know based on this is you cannot use that in an argument. And that's why they call this as just false. Okay? All right. Next. And the converse of if X equals 2, then X plus 3 equals 7. What's the converse of that? Well, if X plus 3 equals 7, then X equals 2. Right? Okay, and let's move on. And it turns out that this is also false. If X plus 3 equals 7, then X equals 2 is also false. A negation of a proposition P, written as that thing, and you must read it as not P, is such that if P is true, then not P is false, and if P is false, then not P is true. Okay, that's a negation. A contrapositive of a conditional if P then Q is a proposition of the form if not Q, then not P. Okay, if not Q, then not P. So let's see. You can write this as not Q implies not P. What is the contrapositive of if X is a poodle, then X is a dog? If you are having any difficulty, let me suggest something to you. Can you identify what part constitutes P? If P, comma, then. So that means the stuff in between the statement if and the comma then, that part is P. Would you agree? The stuff between if and comma then, whatever that is the P. If P, comma, then Q. What follows then is the Q part. So P is X is a poodle, Q is X is a dog. So now all you need to do is, okay, I know Q is X is a dog. I need to know what not Q is. X is not a dog. And P is X is a poodle. What's not P? X is not a poodle. Cool. So we are ready. If X is not a dog, then X is not a poodle. Okay. What about the truth value of this statement? Is this true? If X is not a dog, then is it guaranteed that X will not be a poodle? Yep. So this is true. And the truth is, if the conditional is true, the contrapositive is automatically true. If the conditional is true, the contrapositive is automatically true. Please remember that. Okay? All right. However, if the conditional is false, the contrapositive need not be automatically false. That may be true or false. Okay? A biconditional. A biconditional is a proposition of the form P if and only if Q. This is also stated as P, and you write arrows on both sides, but when you see arrows on both sides, that long equal sign and all that, you read it as if and only if. P if and only if Q. Okay. Now, here is a small problem. Those of you who have grown with English as your language, you are familiar with certain expressions, and you are familiar with a certain usage of some expressions. For example, if and only if. Have you ever heard that phrase, if and only if? Of course you have. What does it mean so far as you are concerned? If and only if is like mom says, hey Johnny, you'll get to play with your Nintendo if and only if you clean your room. Right? That's a finger wagging thing. You better do this, otherwise you won't get to do that. Kind of a deal. But in mathematics, if and only if does not work like that. It has a completely different meaning. When we say P if and only if Q, what we mean is, it refers to a situation where both the conditional and converse are true. What do I mean by that? That means if P then Q is true, and if Q then P is also true. Whenever something like that happens, we say P if and only if Q in a very succinct way. Please understand that one. And you should be able to go both ways. If you find that P implies Q is true, that the conditional is true, and for some reason even the Q implies P is also true, the converse is also true, then you don't have to say in a long-winded way, oh, if P then Q is true, and if Q then P is also true, or man, the conditional is true and the converse is also true. You can simply say P if and only if Q. Cool? There's a way of saying it. P is equivalent to Q. Let's not get into that. So, x plus 3 equals 7 if and only if x equals 4. Right? Can you tell me what this means? X plus 3 equals 7 if and only if x equals 4. Can you tell me, what two things are true when we say this? If x plus 3 equals 7, then x equals 4. That is true. If x equals 4, then x plus 3 equals 7. That is also true. That's what this means. And you would agree that if x plus 3 equals 7, then x equals 4, right? Yeah, that's a true statement. And also, if x equals 4, then x plus 3 is definitely equal to 7, right? So they are both true. And that's why, if you see this, you could have just simply said, oh, x plus 3 equals 7 if and only if x equals 4. Okay? I needed to talk about all of this because we are about to see things where we need this. And I stopped last time with this, and so let's move on to the next slide. Theorem. A theorem, just about every theorem, is in the form of if P then Q, in the form of a conditional. That's why I covered logic. Just about every theorem is in this form. If it is not, then you can always rewrite it in the form of if P then Q. Cool? Okay, so needless to say, here we have bumped into a theorem, and sure enough, it is in the form of a conditional if P then Q. If sigma a sub n converges, then limit of a sub n as n approaches infinity is equal to 0. I'm not going to prove it, but that's a theorem. Is the theorem true? Yep, it's called a theorem precisely because it has been proven to be true, right? You don't call something a theorem if it is not true. Maybe there are some rare cases where there are no rare. Fermat's last theorem, right? Yeah, there is an exception to that. There are a few exceptions like that. Fermat's last theorem was not proved for quite some time until, 1996 or so. But it was called a theorem. It shouldn't have been. It should have been called a conjecture. Anyway, if sigma a sub n converges, then limit of a sub n as n approaches infinity equals 0. Is that true? What exactly is it trying to say? It's saying that if you somehow know that a certain series converges, let's take that as a granted part, then the limit of the nth term as n approaches infinity has got to be equal to 0. You can take it to the bank. There's no mincing words there. Excuse me. So it's guaranteed that in that case, if a series converges, the limit of the nth term will be equal to 0. Okay, let me show an example. Do we know that sigma 0.2 to the n converges? What kind of a series is that? It's a geometric series. What's the first term? Plug n equals 1. 0.2 to the 1 is 0.2. Second term, 0.2 square. Third, 0.2 cube. Oh, okay. So that is a geometric series with the first term a being equal to 0.2, and more importantly, the common ratio r is also 0.2. And what does the convergence of a geometric series depend on? Whether absolute value of r is less than 1. So r is 0.2. Absolute value of 0.2 is 0.2. Is that less than 1? Yes. So this geometric series converges. So according to the theorem, what can we immediately conclude? We can be guaranteed that limit of 0.2 to the n, that is the nth term, as n approaches infinity is equal to 0. Guaranteed. You tell me, isn't that true? Limit of 0.2 to the n as n approaches infinity. Yep, that is equal to 0. Look at the terms. 0.2. 0.2, the quantity square is 0.04, 0.008, 0.00016, and so on, right? Those terms are decreasing and approaching 0. So, that is an example. Now, here is something that I wish all of you would do from now on. Every single time you bump into a theorem, immediately ask yourself, what is the converse of the theorem? What is the contrapositive of the theorem? Okay? And ask whether the converse is also true. And contrapositive, obviously it will be true. When the condition is true, contrapositive is automatically true. And then ask, what are the implications of the fact that the contrapositive is true? And you will gain so much more knowledge by just asking yourself those questions every time you bump into a theorem. Okay? All right. What's the converse of this theorem? If Q then P, right? If limit of a sub n as n approaches infinity equals 0, then sigma a sub n converges. That is the converse. If limit of a sub n as n approaches infinity equals 0, then the series converges. Sigma A sub n converges. So what's the next thing that you should ask? Is this true? I don't know, man. Well, let's see. Can we come up with one measly counterexample? One counterexample for this. What should your counterexample look like? Oh, it should look like when you take the limit of the nth term of that series, that should equal 0. But the series should not converge. You get it? The limit of A sub n must be equal to 0, but then that series sigma A sub n actually does not converge. Do you know of any such series? Harmonic series. Wait. False. Okay. So harmonic series is a classic counterexample for it, because in the case of harmonic series, it so happens that limit of 1 over n is 0, but sigma 1 over n actually diverges. That's the idea. Cool. And that is a very, very, very important thing to know. Now, let's look at what contrapositive of this one is. Maybe I should have not shown it to you. What's the form of the contrapositive for if P then Q? If not Q, then not P. So if limit of A sub n is not equal to 0, then sigma A sub n does not converge, or sigma A sub n diverges, right? Is that true? Yeah, when the theorem is true, its contrapositive is automatically true. So this is true. Now, what a fascinating result this turns out to be. What is it saying? If you take the limit of the nth term and you find that that limit is not equal to 0, you can confidently say that the series diverges. You don't have to do any other work. You can just confidently say, yep, that series diverges. Why? Oh, because I looked at the limit of A sub n and that turned out to be not 0. Oh, okay. End of the story, end of the argument. Now, I don't know how I can stress the importance of this boxed thing. I put 3 stars on it because it's very, very vital that you recognize it and remember it. When limit of A sub n is equal to 0, you cannot conclude sigma A sub n converges. But when the limit of A sub n is not equal to 0, you can conclude the series diverges. Cool? Let's move on. Keep that in mind. Determine if the series converges. If it does, find the sum. 1/3 plus 1/6 plus 1/9 plus 1/12 plus 1/15. Wait a minute. I don't know. Any thoughts? Wait. Does it look like we can factor out a 1/3 out of every term? Yep, let's do that. And so we get 1/3 times 1 plus 1/2 plus 1/3. Okay, how does that help us? Does this ring a bell? 1 plus 1/2 plus 1/3 plus 1/4 plus. Hey, that's a harmonic series. Does a harmonic series converge? Nope. So the sum of this stuff inside the parenthesis, we know diverges. That means because it goes to infinity, that sum goes to infinity. So 1/3 times that also should go to infinity. Therefore, this series also diverges. That's the argument we'll make. Since sigma 1 over n is a harmonic series that diverges, 1/3 times that also diverges. Cool? Any constant multiple. Okay, let me ask you another one. What about this guy? 1/3 plus 2/9 plus 1. Is that a harmonic series? Can we factor out a 1/3 out of every one of them? Yeah, we could. So we get 1 plus 2/3 plus 1/9. I don't know. Give it a shot like that. I cannot see anything based on that. Especially the fact that they're alternating between 1 and 2, 1 and 2 on the top. That's what is a bit confusing. So check this out. Could we pick the odd terms and combine them, and even terms and combine those? Right? Look at how clever we could be. Yeah. And now focus on each one of these things. Each one is an infinite series. 1/3 plus 127 plus 1 over 243. What kind of a series is that? That is definitely a geometric series with A is 1/3 and R is 1 over 27 over 1/3, which is 1/9. Similarly, this is also a geometric series. A is 2/9 and R is also 1/9 for this one. So they are both geometric series with R equals 1/9, except that the first terms are different. And so we should ask, does this series converge? The first one? Yeah, absolute value of R is 1/9, which is less than 1, so it converges. Similarly, the second series converges. So convergent plus convergent is convergent. Why? Convergent simply means that the sum is a finite number, and that's the case for both the series. So if each addend, addend, each addend, I don't know how to pronounce it. The stuff that are adding, A plus B, when I say A and B are called addends. So if A and B are finite numbers, then A plus B also must be a finite number, right? That's the idea. So this converges. And what's the sum? A over 1 minus R. Let's apply that to each one of them, and that turns out to be 5/8. Cool? All right, the series converges and the sum is 5/8. Determine the series converges. If it does, find the sum. Okay. What? Geometric? Nah, it don't look like a geometric series. Harmonic? Nah. What do we do? Wait, can we figure out what limit of a sub n is as n approaches infinity? Okay. Why? What's the big deal about finding limit of a sub n? Is that what you're asking? You remember the boxed thing with 3 stars? What does it say? If limit of a sub n as n approaches infinity equals 0, you cannot conclude anything about whether the series converges or diverges. However, if the limit of a sub n as n approaches infinity is not equal to 0, then you can conclude the series diverges. That's the reason we are looking at limit of a sub n. So here a sub n is this, and limit of a sub n. What is limit of a sub n? We have a polynomial over polynomial, same degree. So then the limit must be the ratio of leading coefficients. That is coefficient of the highest term on the top over the coefficient of the highest term on the bottom, which is 1 over 1, which is 1. That is clearly not equal to 0. Therefore, we can take it to the bank. Recall that from contrapositive, we have that whenever this sigma A sub n diverges, and so our series diverges. Cool. All right. What about this guy? Sine of 100, the quantity raised to n. What's the first term? Sine of 100. Second term, sine of 100, the quantity square. Third term, sine of 100, the quantity cube. Ooh, okay. What kind of a series is it? Do you agree it's a geometric series? Yep. What's the first term? A? Sine of 100. What is R? Sine of 100. Okay. So it's a geometric series with R equal to, whoa. A sub n. Ooh, I'm trying to see if I can do the limit thing. What is limit of sine of 100, the quantity raised to n as n approaches infinity? I don't know, man. Yeah, I know. What is sine of 100? Neither you nor I knows. Okay, calculator. No, don't need to go for a calculator. What is guaranteed about sine of 100, even though we don't know the exact value necessarily? What's the range of sine? Meaning sine values always stay between what two numbers? Yep, -1 and +1. So, can we confidently say sine of 100 must be some number between -1 and +1? Yeah. What is limit of r to the n when absolute value of r is less than 1? Go back to sequences. What is limit of r to the n when absolute value of r is less than 1? 0. So we can confidently say this limit is equal to 0. Right? Cool. We found that limit of a sub n is equal to 0. Can we conclude that the series converges as a result? Yeah, man, when the limit of a sub n uh-oh. Yeah, that kid is cute though. So, no, you cannot conclude that. Limit of a sub n equals 0 does not mean series converges. It may, but you cannot use that as an argument. So, however, we recognize this is a geometric series, and we also recognize absolute value of r is less than 1. Therefore, series converges. And the sum would be sine of 100 over 1 minus sine of 100, whatever that is. We don't need to know the exact value. Cool? Next. Yeah, telescopic series. Find the sum of the series, this. Right? It doesn't look like a harmonic series. It doesn't look like a geometric series. So the question is, what do we do? When we don't know anything about the sum of a series and we want to find it, what was the one strategy that we learned about very first time? Find the nth partial sum s sub n and take the limit as n approaches infinity. Right? That was the first strategy. Let's do that. Let's see if we can find the nth partial sum S sub n first. So to do that, we need to do something. Limit is 0, so inconclusive. Limit of A sub n is 0, so cannot say whether the series converges or diverges. Geometric series, no. So what do? Recall that we find an expression for S sub n and then take its limit as n approaches infinity. Okay. And so that is, let's figure out the partial fraction decomposition of this. I prefer to use that clever method, which makes life so much simple. What is that? If the factors are linear, non-repeating, then we can do this. To figure out what goes on top of n plus 2, set n plus 2 equal to 0. You follow 3 steps. First step, set n plus 2 equal to 0, solve for n, -2. Come to the left-hand side, cover up that n plus 2 itself. That is the second step, covering up. Third, plug the value -2 for n. So having covered up n plus 2, we plug in n equals 2. We get 2 over -2 plus 4. -2 plus 4 is +2. So 2 over 2 is 1. So what goes on n plus 2? 1. Cool. What goes on top of n plus 4? Follow the exact same 3 steps. Set n plus 4 equals 0, first step. N equals -4. Cover up n plus 4, second step. Now plug, third step, plug -4 for n. 2 over -4 plus 2 is 2 over -2, which is -1. In other words, we can write this as 1 over n plus 2 minus 1 over n plus 4, where n is an element of the natural number set. That's a fancy way of saying when n equals 1, 2, 3, 4, 5, 6, 7, like that. N takes on a value in that set. Let's see how that helps us in finding S sub n. So S sub n, recall, is nothing but the sum of the first n terms of the series. The nth term is 2 over n plus 2 times 2 over the quantity n plus 2 times n plus 4. So the first term, plug in n equals 1, 2 over 1 plus 2 is 3, 1 plus 4 is 5. 2 over 3 times 5. We can say that. But there is another way of saying the same thing. What is the first term? Don't use the left-hand side. Use the partial fraction version of it. Plug n equals 1 into this one. Then you get 1 over 1 plus 2, that is 1/3, minus 1/5. So in this case, let's try to use the partially decomposed version of this. 1/3 minus 1/5 is the first term, plus second term. Plug n equals 2, so you get 1/4 minus 1/6, plus 1/5 minus 1/7, plus 1/6 minus 1/8, and 1/7 minus 1/9, plus so on. Right? However, it doesn't continue. We have to stop at the nth term. So that, what is the nth term? This 1 over n plus 2 minus 1 over n plus 4. We have to stop there. So this is what I'm going to do. I'm going to write it all the way to the right in the next line, which is the nth term. And before this, there must have been another term, which is the n minus 1th term. Any idea what that term is? I know. Think about it. What is the term before this one? Well, can we plug n minus 1 for n into this expression? Yeah, 1 over n minus 1 plus 2. n minus 1 plus 2 becomes n plus 1, minus 1 over n minus 1 plus 4 is n plus 3. Cool. So 1 over n plus 1 minus 1 over n plus 3. Right? And the one before that? Well, keep decreasing this one. N plus 2, n plus 1, n. So 1 over n minus n plus 4, n plus 3. So minus 1 over n plus 2. 1 over n minus 1 over n plus 2. 1 over n minus 1 minus 1 over n plus 1. So on. So far, did it make sense? I know we went through quite a few steps, but please absolutely make sure that you understand this part. Why? It is because when we write like this, we see something, which is, hey, there is a negative 1/5 here, and 2 terms later, there is a positive 1/5, right? They add up to 0. Cool. So this negative 1/5 and that positive 1/5 add up to 0. So I'm just going to cancel them. Similarly, there is a negative 1/6 here in the second term, and 2 terms later, there is a positive 1/6. On purpose, I'm saying 2 terms later. Okay, you will see why I said that. And so I'm canceling them. Again, negative 1/7, 2 terms later, there's a positive 1/7. Cancel them. Negative 1/8, well, the thing is, based on the pattern, I can be confident that even though I didn't write the term that comes 2 terms later, there will be a positive 1/8 in 2 terms later. And so I can cancel the negative 1/8 with that unseen, invisible positive 1/8. So that's gone. Same argument, negative 1/9 goes away. You see the logic? So leaving us with, on the top row, 1/3 and 1/4. Now let's come to the bottom row. We see anything? Yeah, we see a 1 over n plus 2 here, and 2 terms before that, there is a negative 1 over n plus 2. So we'll cancel those things. They add up to 0. Cool. We see a 1 over n plus 1, and sure enough, 2 terms before that, there is a negative 1 over n plus 1. So they add up to 0. There's a 1 over n here, and that gone. 1 over n minus 1 here, that cancels out with a negative 1 over n minus 1, 2 terms before this. So this is gone. 1 over n minus 2 is gone in a similar way, leaving us with minus 1 over n plus 3, minus 1 over n plus 4 in the bottom row. So eventually, this is like 1/3 plus 1/4 minus 1 over n. What was our whole objective? Our whole objective was to find the sum of the series. And how did we want to find that? By finding an expression for S sub n and then taking the limit of it as n approaches infinity. Did we find an expression for S sub n? Yes, we did. All that is left is finding the limit as n approaches infinity. What happens to 1 over n plus 3 as n approaches infinity? Goes to 0. 1 over n plus 4 also goes to 0. So all we would be left with is 1/3 plus 1/4, which is 7/12. Cool. A series like this is called a telescopic series. Any idea why it gets that name? Well, it's kind of like this. You remember some older telescopes, like the one that Galileo used and all that? It's like a tube inside a tube inside a tube inside a tube. So you could collapse it when you're not using it, and it would be just about 1 foot long or 2 feet long. But when you're getting ready to view through it, you can pull it out, and it extends into a big long one through which you can look. As you see, that's exactly what we can do here. This S sub n can be written in terms of a whole bunch of terms like that, or we can cancel a whole bunch of them, and then it just becomes these 4 terms. That's why it's called a telescopic series. Cool. What else? Another telescopic series problem. The only difference between the previous one and this one is I started with n with a 7 as opposed to 1. Okay. That again, the concept is same. Do a partial fraction decomposition and write it like this. The only place that you need to be careful about is when you're writing S sub n, what do you plug in for n, the first term? To get the first term of this S sub n, you need to plug n equals 7. Okay, so making it 1/2 minus 1/3 to be the first term. That's the only difference. Don't go plugging in n equals 1 and say 1 over -4 minus 1 over -3, man. No, man. Okay, so 1/2 minus 1/3. And then plug n equals 8 to get the second one, and so on, right? And similarly, write the bottom row terms and recognize that -1/3 cancels out with +1/3, -1/4 is the next term with the next term, and blah blah, and a whole bunch of things cancel, leaving us with only 1/2 minus 1 over n minus 4. 1/2 minus 1 over n minus 4, and take the limit of this as n approaches infinity, and you get, ladies and gentlemen, 1/2. So the sum of this series is 1/2. It's another telescopic series. Cool. All right.